Your choice to click on this video was predetermined billions of years ago, at the moment of the Big Bang. As strange as it may sound, this conclusion can indeed follow from certain theories or their interpretations. We are discussing how the emergence of simple life on our planet, followed by complex life and eventually us, is an extremely unlikely event, and that for it to happen, lots of factors had to align. But what if it couldn't have happened any other way? Now let's switch gears to something that seems completely unrelated, to strange quantum stuff. Einstein strongly disliked the so-called spooky action at a distance, a quantum effect that appears to violate rules and the limit of the speed of light. As strange as these effects related to quantum entanglement may be, with the instantaneous change in the state of the entangled particle when we measure the other, they are real and have been confirmed repeatedly through experiments. But the true nature of this phenomenon, why it actually happens, remains unknown to us, though there are some theories. And one such attempt to explain these effects is superdeterminism. It's like determinism, only super. But let's not rush things and try to sort it all out step by step. Today we'll talk about what determinism and superdeterminism are, and how superdeterminism explains some of the problems in quantum mechanics. Do we have free will and the ability to make independent decisions? What do scientists and philosophers think about this, and how is it all connected? I'm Andrei, and this is Cosmos Elementary. Do we really make our own decisions? This question has occupied the minds of scientists and philosophers for more than a millennium. But what does it have to do with space at all? Well, according to some scientists, whether we have free will or not directly depends on how the universe is fundamentally structured. And that's exactly what we're talking about today. Actually, it's a great way to spark a heated debate between a couple of scientists and/or philosophers. Just bring up the question of whether free will exists. At the same time, for most of us, this question might seem absurd. Of course we have free will. We make our own decisions and choose what feels right to us. But according to some scientists, the very laws of physics suggest that we are not free in our choices. And if that's the case, then a whole bunch of moral, ethical, and existential questions immediately arise. However, the complexity of this question begins right at the point of defining what free will actually is. In simple terms, it's our ability to make a specific choice and control our actions. Say you want a snack, and your choice is between a bagel and a banana. Let's say you pick the banana. That's your own choice. You decided that. And if you could go back in time and wanted to, you could have chosen the bagel instead of the banana, right? Well, it's not that simple. I already mentioned that debates about this have been going on for more than a millennium. But what interests us most is what modern science has to say about it. And from its point of view, some doubts about whether we're truly free in our choices don't start on the scale of the universe, but right here. I mean, with how our brain works. Neurobiology isn't what I'm really familiar with, but since we brought it up, we can't ignore some research in this field. You may have heard that some neurobiologists have supposedly proven that free will is an illusion. This story dates back to 1980s. In 1983, neuroscientist Benjamin Libet conducted his famous experiment. We won't go into the details here, but the main point is this. Libet seemingly managed to record brain activity in his subjects that he called readiness potential. This activity occurred a couple of hundred milliseconds before they made a conscious decision. And this can be interpreted to mean that the decision is made in our brain before we become consciously aware of it. So it seems that we only think we make decisions ourselves, and free will is an illusion. But the question is, does this readiness potential really mean exactly what Libet interpreted it to mean? In fact, some later studies disagree with those conclusions. That is, the activity does exist, but it might simply be preparation for a spontaneous decision or the result of other factors. In general, the idea that we become aware of our decisions only after the fact, with a noticeable delay after they have already been made, sounds interesting and in its own way frightening. But it can hardly be called a fact, or even a widely accepted theory among most scientists. But what we're really talking about today is an even deeper question. What if your choice to eat a banana instead of a bagel wasn't just made slightly before you became aware of it, but the reasons behind it can be traced all the way back to the beginning of the universe? Another thing about nature, and even about the very existence of which scientists and philosophers have long debated, is time. In my video about the nature of time and whether time itself could be an illusion, I talked about different perspectives on time. And one of the approaches I mentioned is eternalism, from the word eternal. This approach is also called the block universe. Why is it called that? Because in this case, the universe is represented as a four-dimensional block, with 3 spatial dimensions and 1 time dimension. This is of course a simplified illustration where 1 spatial dimension is removed for clarity. One of the main ideas here is that the past, present and future all already exist and have always existed. They exist simultaneously. And we simply move through it, living behind the past, which does not disappear anywhere but continues to exist, which in theory could make time travel to the past possible, though even then we still wouldn't be able to change anything. But even more interesting is that the future already exists too. And since it already exists, it cannot be changed. It is predetermined. In this version, our life is more like not a game with branching scenarios where we can make decisions that lead to different endings, but like a movie that we watch passively, merely indulging ourselves in the illusion of free will, which we actually don't have. It may seem to us that there are many possible versions of our future ahead, but in reality, there's only one. Sounds depressing. Fortunately, the block universe is not a widely accepted theory, and there is no evidence to support it. There's also a less radical version called the growing block universe. In this version, the past is preserved, but the future does not exist yet, so it is not predetermined. In fact, much of the research concerning free will focuses on whether the existence of free will can be reconciled with causal determinism. From the Latin determinare, to determine, to limit, there are different types of determinism. But causal determinism refers to the idea that the future is completely determined by the past and the laws of nature. From here on, I'll just say determinism. Can we predict what will happen to this ball when I let go of it, based on its current state and our knowledge of gravity? Of course we can, if nothing interferes with our system. But let's make the example a bit more complicated. Let's say somewhere in space there is a container with a number of balls inside. They are moving chaotically, flying in different directions and colliding with each other. We know what state they were in a day ago. Can we accurately predict how the container and the balls inside will look a day from now? Obviously, it's more complicated here than with just one ball. But is the difference basically only in the amount of calculation required? Let's assume we have a complete description of the system exactly as it was a day ago. We know the direction and speed of every ball, all their properties, visible and invisible effects, absolutely complete information that could possibly exist. In addition, we know all the laws of nature that govern these balls, and we know all the formulas that describe these laws. Next, we take all the information about the system's state from a day ago, plug it into the formulas we have, and if our information is truly complete, then we will be able to predict with accuracy where each ball will be and what the system will look like a day from now. And not just a day. What about 100 years? Assuming nothing interacts with the system from the outside. It turns out that the system has only one possible future. This future is predetermined. When we talk about determinism, the same logic applies not to just a bunch of balls, but to the entire universe. After all, if we look at the universe from the perspective of classical physics, what is it but a bunch of particles constantly in motion? Of course, nowadays we have a more complex view of the universe, but we'll get to that a little later. By the way, this kind of logic allows us to create scientific simulations of the universe, where we observe how many particles behave and what structures they form. Of course, in this case, we use our limited knowledge of the laws of nature. Now we can recall a thought experiment known as Laplace's demon. I mentioned it a while ago in my video about the black hole information paradox. In this thought experiment, one can imagine an entity, a kind of intelligence that possesses information about every particle in the universe and has complete understanding of all the physical laws. And of course, we must also assume that it can process such colossal amounts of information. Then in theory, such an intelligence could predict the future of the entire universe at any given moment. It seems that from simple particle interactions, an entire universe emerges. Planets, stars, galaxies, complex systems, life, and all of it is completely predictable. As a simplified example for such reasoning, one can use the game of life. It's often mentioned when discussing the question of free will. The game of life isn't something like The Sims, it's a type of cellular automaton invented by mathematician John Conway. The game consists of a grid of cells, which can be either finite or infinite. Although there are now 3D versions as well. Each cell can have only two states: alive, that is filled, or dead, that is empty. And there are just 4 rules. The first one: any alive cell dies in the next generation if it has fewer than 2 alive neighbors. Kind of like from underpopulation. You place a cell and add 1 neighbor. When you run the simulation, both die. But if you add 2 neighbors, the original cell survives. The second rule is, if an alive cell has more than 3 alive neighbors, it dies kind of due to overpopulation. You added 4 neighbors and after a couple of generations, all the cells died. The third rule follows from the previous 2. Any alive cell with 2 or 3 alive neighbors survives unchanged to the next generation. The last rule: any dead cell with exactly 3 alive neighbors becomes alive in the next generation. So we place 3 cells around the dead one, and you see it comes to life, though not for long. The initial conditions on the grid, the first generation, are set by us. But from that point on, evolution is entirely governed by the rules we mentioned. The goal is to discover interesting patterns and observe their behavior. Here's a simple example. We place a small cross shape, start the simulation, and boom, it expands and then gets stuck in a repeating cycle. You can place a bunch of alive cells in random positions and just sit back and watch how the grid evolves. People have been doing this for decades. And by now, many fascinating patterns are known, ones that can move, shoot, change shape, and so on. Online you can find plenty of examples of interesting scenes in the game of life. I'll leave a link to a web version of the game in the description. Feel free to get lost in it yourself. So here, on a simple grid, with simple rules, we get interesting and even complex objects that display certain behaviors. And yet the system is completely deterministic and predictable. If we know the rules and the initial conditions, we can precisely calculate the second, third, or even 123rd generation. That's exactly what the algorithms do here. So what if the entire universe works the same way? Sure, a being like Laplace's demon is impossible, because such level of computation simply isn't feasible. But just because we can't obtain all the information about the universe and precisely calculate the future doesn't rule out the possibility that it is predetermined, like in the game of life. I'm sure many of you already have a few objections to this line of reasoning, and we'll talk about them. Intuitively, it seems that it is one thing when we talk about flying balls and quite another when it comes to complex systems like a human being or the human brain. And yet, this classical deterministic approach is applied to humans as well, and accordingly to their decisions. After all, our brain is also made up of particles, and these particles obey the same laws. And if we go back to the example with our choice between a bagel and a banana, we can try to trace the chain of events that led us to pick one or the other. Psychological causes triggered the feeling of hunger in us, and all of this also operates according to certain laws of nature. Certain causes and events in the past pushed us towards a specific choice. It's all the work of neurons in the brain, which themselves follow certain laws influenced by prior events. You can trace it back all the way to our birth, and then even further to the birth of our ancestors. The entire history of human civilization, the evolution of life on Earth, the formation of the solar system, galaxies, and the universe itself, every event was preceded by another event, and it's all the interaction and movement of particles. Our bodies themselves are made of atoms forged deep inside stars. In short, billions of years ago, one particle collided with another, that one with the third. Billions of years passed, and now you think you choose the banana and could have chosen otherwise, but of course, few people will like that idea. But that's basically how it would have to work if our universe follows deterministic laws. You might think there are different possible futures where you act one way or another, but in reality there is only one. Even events that seem random to us are predetermined. When we roll dice, we can't predict with certainty what number will come up. However, if we had complete knowledge of the die's initial position, how, where, and with how much force it was thrown, everything about the environment, and accounted for all possible forces, in theory we could calculate the outcome. And some of the successful theories that describe the universe are deterministic. For example, general relativity. Although there are certain situations even in classical theories where determinism is called into question. But some of you have probably been shouting at the screen these past few minutes, what about quantum theory with its probabilities and randomness? Indeed, what's going on with quantum stuff? At the end of the 19th century, when scientists described the universe using the quite deterministic Newtonian mechanics and Maxwell's equations of the electromagnetic field, many scientists considered the hypothetical existence of something like Laplace's demon. But then quantum mechanics came along with all its weirdness, and it pretty much turned our understanding of how the universe works upside down. I've talked about various quantum effects, including quite recently in my video about the depth of the universe, so we won't go into detail here. From the perspective of quantum physics, the logic we used earlier with flying and colliding particles starts to seem like it doesn't quite hold up anymore. Yes, maybe for large objects, we have gotten pretty good at predicting the positions of planets, and we can even predict events like, say, occultation of Betelgeuse by an asteroid. But when we zoom down to the scale of subatomic particles, they stop being just very small moving balls. And fundamentally, we cannot know complete information about a particular particle. Heisenberg's uncertainty principle tells us that it's impossible to know with absolute precision certain pairs of parameters of a particle simultaneously. For example, when it comes to an electron, we cannot know both the exact position and its velocity at the same time. The more precisely we measure one parameter, the less precisely we know the other. And let me remind you that electrons in an atom are no longer described as distinct balls orbiting the nucleus, but rather as an electron cloud, where the electron's position is defined only probabilistically. The whole story is that at a quantum level, particles exist in superposition. That is, they can be in multiple states simultaneously and only take on a single random state when we observe or measure them. And just to clarify, the role of observation does not necessarily have to involve a conscious observer. This quote-unquote measurement can simply be an interaction with the environment. This ties into the principle of realism, which states that the properties of objects exist independently of observers and our minds. They are real in the physical universe. All this strangeness around the role of observation and measurement leads some people to think that reality itself is subjective, dependent on observers, that we even create reality by observing it. But that's more of an extreme view. Another example of seemingly random and unpredictable phenomena is the decay of radioactive or unstable isotopes. These isotopes decay over time, and I mentioned the concept of half-life several times before. And if we look at a table of half-lives like this one, we see that some isotopes decay quickly, in fractions of a second, while others take much longer, up to billions of years. But notice we don't say decay period, but rather half-life, which we usually describe as the time it takes for half of the isotopes in a given amount of material to decay. Although even that isn't a perfectly precise definition. We don't know and we can't know when a particular atom will decay because nature of decay is probabilistic. The half-life of carbon-14 is 5,730 years, meaning that the probability that a single atom will decay within that time is 50%. For a larger amount of material, we're talking about an average value, but each individual atom may live longer or shorter than that. We cannot predict exactly how long, and this reflects the random or probabilistic nature of the process. And on top of it, in the quantum world, the principle of locality seems to be violated. According to this principle, an object is influenced directly only by its immediate surroundings. For one particle to influence another, they must interact directly, or that influence must be transmitted by another particle or a wave. And naturally, the speed of this transmission is limited by the speed of light. But today I already mentioned the so-called spooky action at a distance. If we take two particles, whose states we don't know, for example, they are in superposition of states A and B, and entangle these particles, then separate them by distance, and when we measure one particle when it takes state A, the other particle immediately assumes state B, and we instantly know this, even if the distance between the particles is 100 light-years. It seems like this violates the speed of light limit and the principle of locality. I talked about this in more detail in my video about teleportation. And this isn't just some theories and calculations, and I say this without any disrespect. Many quantum effects have been confirmed by countless experiments, and quantum mechanics makes quite successful predictions in certain areas. And this probabilistic nature of the quantum world seems to break determinism. That's why quantum physics is often called non-deterministic. By that logic, since many things happen randomly at the quantum level rather than strictly according to what came before, Laplace's demon would be impossible. And so, our free will is saved? Well, it seems that the view that we have no free will at all isn't very popular among scientists and philosophers nowadays. In a couple of surveys I found only about 10 to 15% of people strongly reject the existence of free will. But in that smaller camp was, for example, Einstein. He really disliked all this spooky action at a distance. You might recall his famous quote, "God does not play dice." Because all of these oddities in quantum mechanics, Einstein believed that the theory and our knowledge of the processes occurring at microscopic scales was incomplete. Could there really be something we don't know, something that explains these oddities and makes them predictable? In principle, yes. And this is usually where people talk about so-called hidden variables, parameters we don't yet know about that would explain quantum weirdness and restore determinism. However, many scientists seriously doubt the possibility of such parameters existing. But it's not that simple. For example, the Schrödinger equation, which describes the wave function of a quantum system and is one of the cornerstones of quantum mechanics, is called deterministic. Moreover, quantum mechanics has many interpretations, and some of them can be deterministic, though some achieve this in quite radical ways. For example, the many worlds interpretation. According to it, when a quantum particle takes one of its possible states, at the moment, another parallel universe is created, where the particle took a different state. This interpretation is both deterministic and local, but the problem is, it currently has no experimental support. Another approach to this question isn't about which interpretation of quantum mechanics we use, but rather this. Let's say that at the quantum level, probabilities really do rule, and there is a lot of randomness in the behavior of tiniest particles. But at the larger scales we observe every day with big objects, we usually don't see quantum effects. Sure, electrons may be flying around in their electron shells and probability clouds, but knowing all the parameters, we can easily calculate how 2 billiard balls will roll after a collision, right? In that case, despite quantum randomness, our everyday world might still be deterministic. And then again, we wouldn't have free will. The question is so complex and important that among scientists and philosophers, there are several schools of thought viewing it differently. For example, compatibilists believe that even if our world is fully deterministic, free will can still exist. How exactly? That's another question. It's worth noting that a significant number of specialists identify with this view. But what is superdeterminism? Superdeterminism is one way, alongside interpretations like many worlds, to preserve realism and locality. We've already discussed what regular determinism is. The universe works like a mechanism where every subsequent action and event is predetermined by the previous ones. And this idea doesn't quite mesh well with experiments on quantum systems, all those quantum entanglements, superpositions, and wave function collapses. So superdeterminism suggests that the universe is not just deterministic, but, as you might guess, super deterministic. It seems to us that scientists freely choose how to conduct experiments measuring seemingly random quantum events. But the universe is so deterministic that it forces the experimenters to select and perform experiments in ways that are consistent with other measurements. If we recall the example with quantum entanglement experiments through the lens of superdeterminism, it's not that we measured one particle and instantly found out it's in a state A, while the other particle immediately took state B via spooky action at a distance. Instead, the state of each of the two entangled particles was predetermined all along. The universe knows, and always knew what states those particles must be in. The true states of the particles, which we only discovered after measurement, were hidden from us by quantum mechanical effects. The quantum world only seems random to us, and we can't predict some phenomena simply because we don't have all the information, the very hidden variables themselves. The concept of superdeterminism was formulated by John Stuart Bell, the author of Bell's theorem, in the 1980s, surprisingly during a radio interview. When asked how determinism could be preserved in the universe, he replied, and I quote, one of the ways of understanding this business is to say that the world is superdeterministic. That not only is inanimate nature deterministic, but we, the experimenters, who imagine we can choose to do one experiment rather than another, are also determined. If so, the difficulty which this experimental result creates disappears. Overall, it's clear that many don't like this view. It seems to take away our free will and choice. Some say that this approach kills science. It's not a very pleasant thought that you're not really in control of your own decisions. Then there is the moral question that often comes up, that no matter what immoral actions we take, we could just blame determinism. That it's all predetermined by the universe and we aren't responsible for anything. Among the perspectives, there is also the approach of the illusionists. Not magicians, but those who believe that even if we don't have free will, we should live and think as if we do. Supporters of superdeterminism are few, but they do exist, at least from a scientific standpoint. Among the most prominent supporters is the German theoretical physicist and lately somewhat controversial YouTuber Sabine Hassenfelder. She and her colleagues published scientific papers on superdeterminism, and on her YouTube channel she has several videos dedicated to this topic and to free will. Recently, she had a discussion about it with Alex O'Connor. I've already mentioned, the question of free will has been debated for thousands of years, but scientists have joined the discussion with concrete theories, methods, and experiments relatively recently. We still don't have a definite answer to whether everything in the universe is predetermined, and it's hard to say if we ever will. Personally, I kind of like the illusionist approach in this regard. What difference does it make if everything is predetermined or not? as long as we feel our choices are free. It's better to act as if we have freedom, regardless of whether our decisions were influenced by particle collisions billions of years ago or not.